You have to listen to it twice. So yes, you have to go through the final assessment details and policy, read it carefully, see what it is. It's going to be completely detailed information about the test over here. What are the coding styles, integrity statement, and everything. You go through all the integrity statement and the questions. You answer the questions one by one exactly as is in the policy. After going through all the questions, you submit them. You have to get 100% in it, which means everything must be answered correctly. After you do that, then the test opens to you and you can actually access it. Now, what do we have on the test? I will mention it in detail when the time comes. Okay, I just wanted to make sure I'm not putting this up. Okay, so I'll give you an introduction, and I'm going to say you're tasked with processing whatever stored in a binary file. Each record has presented the other. So essentially, you're dealing with a binary file. You're going to have a binary file. Then, as you did today in your quiz, that you are writing a function that the function reads chunks of the array. You're going to write a function that reads chunks of the file. So you have to do seek G and seek G and things seek G to skip to specific position in the file and read that chunk. So as you have done with the array, chunks of the array, you read that thing in parallel and bring it in. So so you create a function that can actually read chunks of the information from the file. Then you call that file and fetch all the information from the binary file in a multi-threading application. Okay? After doing that, you write a main program that does, again, a filtering over there and gets a subset of the information in the file and extracts it and gives it out. You are to use exception handling. If something goes wrong, you've got to throw exceptions and stuff. And you are to use an STL library in it too. Okay? For the STL library, I will give you the STL library and its reference. So I'm going to say use this one, and I'm going to say this is the STL library. These are the information that it received. This is its description. These are the arguments. So what are the arguments and all the good stuff that it needs to have. So you don't bring your reference sheet for the STL that I'm giving you. You're going to have a reference that tells you exactly what is the STL and what are the arguments that is passed to it and what does it do. I may even give you earlier that what is the STL so you can actually go read the reference for it. So you can actually learn how to work with it. I have to think about it. That's that. And then you have series of concept questions, multiple choice. You have walkthroughs with small, short answers that it generates 3-4 characters based on what you're supposed to do. And they are all from the week 6 and later. Okay? 6 and later. So not from the first half of the semester, second half of the semester. Again, the detail will be in there, so you will see exactly what is it from. And you're going to see that in the agreement. So in the agreement, everything about the test is there, and you know it. And that's that. Any questions about the concept and the programming? It's not up to you. I think I'm going to give you the easy one. I think I'm going to ask you to use async, because threads are not taught that much in the notes as you see. Async is, so, and async is easier. So I'll give you async. So use async. Go study it. What else? That's it? Okay. So now that we have that, let's dig into what we need to cover. So essentially what we have to cover, let me just bring it up. Things we have not talked about. Usually, when I'm teaching 3, 4, 5, I tell to students that it's very possible that we don't cover everything. But I think this semester we can actually. So we started bitwise expressions and understood how they work. Multiple inheritance, we went through it already. Preprocessor directives I did not talk about. Linked list technology, I talked about it a long time ago. I gave you a sample for a queue and stack. That's essentially what it is. I don't know if it's needed to go through it again, but if we have time, sure. And other topics is nothing. So bitwise operators, the only thing that I think it's important for you, so this is what we talked about when we dealt with bitwise operators and everything like that. What you need to know about bitwise operators is this. So we talked about let me see where's the main? Oh, okay. So we just shifted left and right, and that's all we did, right? Nothing else. Did I do and or for you? I didn't do and or stuff, did I? We did? Okay. So I don't think I mentioned to you what is not. Not I did not mention. So again, if I have B as 2 over here, so I'll bring this down. Now I can say B is set to not B. So the thing that you use for destructor, that's bitwise not. If you put that in front of B and show it, you will see, this is what we had from last time, so I'm going to remove it. We don't need that. So when I run this, you'll see that it actually reverses everything inside the, oh, I didn't show the previous one. So I need a bit pattern over there too. So when you do not, it essentially switches all the bits. You see that? Okay? So, and let's bring this back over here. Copy. And what I'm going to do is this. So in here, I'm going to say C out B. And at the end, I'm going to say C out B again. Take a look. Okay? So when you flip the bits and add 1, that's 2's complement. B was 2. I flip the bits, I add 1 to it, it became -2. You follow? That's how negative numbers are designed in C language. We do not have, I think I mentioned to you that we do not have any negative numbers in C language. Everything is positive. To simulate it, they do it this way. So if you actually add those two up, the first row and the third row, the first 2 becomes 0, 1 and 1 becomes 10, 0 goes up, carries 1, 10 carries 1, 0 carries 1, and all goes zeros to the end, and the 1 at the end falls into what we call a bit bucket. And therefore, the result will be 0. Because value A plus value B became 0, it means 1 is negative of the other one. Right? And that's how negative numbers are made in C language. Okay, just keep that in mind. So as you saw in here, I flipped this, kind of flipped all the bits, and I added 1 to it, and it became -2. Okay? So that's that. Another thing we need to learn in C language is it is in C++. It's nothing new in C++, but in C++, and also C, we have what we call a bit field. Because it is very difficult, let's say I want you to, let's say, first of all, I'm going to use the word word, W-O-R-D. Word in assembly language is essentially one integer, one standard size integer. They call it a word in assembly. The reason I'm not using int, because when I say word, it means, for me, it's important, the bit pattern is important, not the number. If I say integer, it means that 32 bits correspond to an integer value. But when you say one word is 32 bits, and each bit means something. Completely separate meaning for each. For example, the status word of the keyboard is the one that I mentioned to you. You can, when shift is pressed, one bit goes on. When shift is released, it goes off. So you can actually detect if the shift is pressed or not. Did I mention to you that? So we used to do cool things. I would say, just to show off, we would say, press the left shift to continue. Like such a thing. Imagine you can do that. Press the left shift to continue. Shift doesn't correspond to any keystroke, right? It's shift and something means capital or lowercase. Or hold left and right shift to stop. Things like that. So you can actually do it. How you can do it? You have to find out go Google it, see what is the address of the status word of keyboard. It's somewhere in memory. So anything you hit word, like Control, Shift, Alt, Windows key, all those things that you hit, it flips one bit on and off. And if you continuously check that, you can actually do stuff with it. Anyways, what I'm saying is that when we are doing stuff like this, it is important for you to know the value of bits number 7 to 11. 7, 8, 9, 10, 11. 5 bits inside the word you need to focus on. Now, you can do it using shifting and stuff, but it's very difficult. Just imagine if you want to know what are the contents of bit number 6 and 7, what you need to do is to first isolate those, which means you have to create a word that only has everything as 1, as everything as 0, except the numbers, what did I say? 6 and 7. Then you have to AND this to your word and see what is the result. Therefore, you will only get the values of those 2 bits. Then you have to shift it all the way to right so it comes to the edge. Now you can see what the number is and understand what the value was. It's crazy. For that, C language has what we call a bit field. In a bit field, it's a structure that is essentially the size of an integer. And within, you can tell what do you want. So for example, I said bits, I forgot, 6 and 7? Okay. So what I need to do, I create struct 6 and 7. Okay? I do something like that. Then I don't need the first, so I said 6. I don't need the first 5, right? So what I will do is this. I'm going to say, int filler, and I'm going to do like this. So 1, 2, 3, 4, 5, right? So I'm going to say 5. Then I'm going to say int 6 and 7, okay? And I'm going to say 2, all right? This means, and the rest I don't care. This means bits 5, I skipped 5 bits, and bits 6 and 7 is now an integer for me. An integer with 2 bits. What does it mean? That 6 and 7 can be 0, 1, 2, or 3. That's it. You cannot put 4 in it. If you put 4, it overflows. Because the size of 6 and 7 over there is 2 bits. So essentially, you can actually set the value to whatever you want. I'll demonstrate. Okay, so I'm going to create a union. I'm going to call it a pack. And in this pack, I'm going to create a 6 and 7. A 6 and 7. 6 and 7, let's call it like this. Then I'm going to have an unsigned int total, okay, or all bits. Okay, now in my program over here, I have that bit pattern thingy, I'm going to keep it. I have that bit pattern thingy, I'm going to keep it. So in here, I'm going to say pack. I should make it capitalized. Okay, I'm going to say pack. And in that pack, I'm going to say pack p. Okay, now I'm going to say p dot all bits is equal to 0. So I set everything to 0, right? Now I'm going to say p dot ss is set to 3. Why is it giving me an error? No. What are you talking? No. No, what did I do? Oh, no, this is correct. Oh. 6 and 7. Sorry. So I've said PSS 6 and 7 is 3. Okay? P, pack, 6 and 7. In 6 and 7, I have these two fields. Now, I'm going to show that with my bit pattern thingy. So in this bit pattern, I'm going to say P dot all bits. You see? It's 6 and 7. And I can set it to, so I don't need to shift left and right and things like that. I can make the pattern that I want with a bit field, say, and that's what you have in iOS when you are opening and closing a file. You say iOS out, then you put an OR. iOS in, you put an OR. You say iOS append, iOS trunk. You OR them all together. These are masks that you're setting something with. And each one of them has a value like that. Like this, you can actually detect. So if you are having, for example, when you look at the documentation of the keyboard that you have, you create a bit field, and you say, OK, integer L shift 1. It means it becomes a Boolean. You can actually set a Boolean for it. So you can access only that bit, and you can set it to 1 and 0, which means you have an integer with only 1 bit, 0 and 1. And this one is 2. So you can do many things in here. I can have, I call this 6 and 7. But using bit fields, what you can do, you can pack stuff together when you're in short of space. So you are programming this. This is a computer. You know that, right? There's a microcomputer in here. You're programming a mouse, and its memory is 2K. It means 2,046 bytes, not like 5 million. Literally 2,000 bytes of memory you have. Now, if you want to have something like coordinates, an integer is 4 bytes. Why you want to waste it? You can have an integer. In that integer, you can say, I want 256. So that's 7 bytes, 7 bits. I'm going to use that one. So you can actually break down an integer into small pieces and use exactly to the size that you want. If you want to hold an employee's record, instead of having an integer for age, an integer for number of integer, a number of children, a boolean for this one, boolean is an integer, number of children is an integer, age is an integer. That's 12 bytes. For all this, you can use one integer. Age cannot be more than 128 years, and that's what, 6 bits? So you create a bit field, and you create age only for the first 6 bits. The person is married or not. That's one boolean. 1 bit. You don't need to hold a boolean for 32 bits. You can pack everything into a bit field and hold only one integer to hold several things in it. And your database will shrink, your memory is going to be less, and the processing time will be faster because you are passing less information back and forth. And that's the good things about bit fields. So bit fields are used for efficient storage of multiple small fields that we said, for flags, device registers, packed structures, and things like that. Be careful. It is a non-portable layout, which means you cannot it's not standard. You set a bit field to something, and that's what you have. You need to have that definition of bit width carried with you from header file to header file to be able to use it. It's not something universal, and it's been there since forever, so any C++ that you're using is going to work with it. Yes?
But you mentioned how everything is split into bits.
Pardon me?
But I once read that the lunar landing, the code works superbly on.
Oh yeah, well, not now. Now they're, you know, but the drone that they sent to Mars, it's essentially a few cell phones in it, literally. Like Samsung something and Google Pixel something. So they actually use the CPUs of that. It's literally off-the-shelf stuff. They put it together. And it worked for a long time. Still, it's actually sending data. So yeah, anyways. So that's that. So we know it. What else? Next thing about exclusive OR, it's a weird thing. You can use it for many things. I think I explained that it's the basis of encryption, right? I mentioned that. Do you remember? Basis of encryption. Huh? One more time.
It was like a tangent from someone else asking something different.
Yeah. So bit fields in here, I'm going to say. So when you are, just to show you something, what exclusive OR can do. Say you have value of 2 integers and you want to swap the 2 values. So what do you write? You write void swap integer reference A and integer reference B, right? So what is the algorithm for this? You put a temporary. No, you don't need to. You can just use these 2 without the third one. So what you can do, you can say A is set to A exclusive OR B. Then you can say B is set to A exclusive OR B. A set to A exclusive OR B. And there you go, the values are swapped. Why? Because of the key effect that I told you. Remember that I told you when you have a data key, I told you when in the basis of encryption is that when you have encrypted code is data exclusive OR to a key. Remember that? And when I said to extract the data back, data essentially becomes the exclusive OR thingy with the key. So essentially, if you exclusive OR back a data to a value again, they switch the values, and that's exactly what happens. So exclusive OR A and B sets the A to B, and then B to A, and A to B, and then poof, the values are exchanged. That's why if I do this, X as 20, Y as 30. So I can actually say swap X and Y. And we get, no, we don't get that because I changed the bad file again. I don't learn, man. I don't learn. Copy. Control Z. Okay. What I meant was this. So now if I run it, you'll see that the values change. See? Without a third variable. This is extremely common in assembly language. Like, you don't want to waste another integer to do something like that. And that works for anything. So if you have humongous amount of data, you can exclusive OR all the chunks back and forth, and it's going to replace. Just divide it into pieces of several integers, and you can do it, and you're done. So that's all about bitwise operators. And we have a few more minutes. We talked about, so this is XOR. We talked about conditional programming. In IPC 144, we started writing, safeguards for our header files. Remember? We say, if not define this, define that. So the hashtags that you are writing in C language, as we mentioned before, you're actually writing another language. It's not C anymore. You are writing the language of the compiler. So you're essentially telling to the compiler what to do before compilation begins. And that's what we are going to talk about the next day you're coming in, because it's way too long to be talked about for in 5 minutes. I'm just going to demonstrate one thing to you. I don't know if I showed you like this long time ago when we taught OOP344, not OOP345. This was the project for it. Okay? Now, this project was a simulation of Windows, but in text space. Did I show you this? So students were supposed to write a program that simulates, you see that? And it shifts to left and right. So literally it's a text box over there, and it goes to the next one. Now it's option that you can change. And I can press F1. This is help that is coming in. So I can press F6. Now, shoot, F6 is captured with this stupid thing, so I cannot demonstrate that. Let me see if it's going to. I can't. Anyways, if I press F6, you will see that I could actually move that thing around like a window. And things like opening a menu. You see, so what essentially demonstrates, so we created this as our project. But the cool thing about it was not creating this. It was the fact that it ran on many platforms, which means I could take this code and put it on a Mac computer and compile it, and it would run on Mac. I could move it to Linux, and it would run on Linux. How did that work? It was using this. So essentially, what we did was this. We said, if defined Borland, then I defined what is the platform. So you see BIO platform. I call it Borland. So this will be defined to Borland. If it was Microsoft, it will define Microsoft. If it's Mac, it will be defined as Mac, Unix, because Mac is Unix. And if it was Linux, it will be set to that one. So we would say if it is Linux, the header file that should be included is this. If it is, so I included this instead of the header file. So at compile time, it would decide what is to be compiled. And in the class, we would just write the prototype of the functions. This is the number of rows of the screen, number of columns of the screen. This is to pause, alarm, get key, do the basic input-output for a screen. And then we built everything over it. But the cool thing is that if you look at the console, for example, clear has many different definitions. One definition is for if the platform is Linux or Unix, then clear is erase and clear buffer. But if I'm on Microsoft, clear is create a D word, character that, coordinate this and that, fill console character with that. So the definition of clear will change depending on platform. And that's preprocessor directives, which means before I process and compile the code, I will ask compiler to which parts to ignore and which parts to compile. Therefore, the code becomes portable from one platform to another. Okay? And that's essentially multi-platform programming. But we have many more things that we can do. We can tell the compiler to do many things. And I always tell this story, and I have 2 minutes to tell you this. 30 years ago, 25 years ago, back in my home country when I came from, when I studied computers. I studied actually mathematics, but applications of mathematics and computers. We had this genius guy who was studying programming somewhere and was like God to us. Like if you've seen Big Bang Theory, that was like Sheldon for us, okay? So this guy, with preprocessor directives, wrote a program that you could compile Visual Basic using C++. So it will actually compile Visual Basic code in a C++ compiler and run, just with preprocessor directives. It was crazy, but it's possible. That's what I'm saying. It's an extremely powerful thing. What you see is powerful, but you can do things that you won't believe. Now, it wasn't Visual Basic, it was Basic language. At that time, we didn't have Visual Basic, we had Basic. But it's just, anyways. And with a compiler of one language, you could compile something. Anyways, so the next time that we are coming to the class, I'm going to teach you macros, how to create macros. With macros, you can actually create function-like things that are not functions. Essentially, you write a piece of code, and you say whenever it wants to be used, expand this one over there, and makes your code faster and life beautiful. So the next day you are coming in, we're going to talk about preprocessor directives, a little bit of pointer to arrays, and that's going to be the end of the story. Okay? Questions? Suggestions? Objections? Good luck. Have yourself a beautiful day.